All right, we're here to talk about troubleshooting Wi-Fi up and down the stack, a philosophy of troubleshooting. Now, we're going to spend most of the time today dealing with the philosophy of troubleshooting. And then on, I believe it's Thursday of this week, we're going to get into some depth of discussions on how the higher layers of the stack impact wireless performance and functionality, because it's something that we miss a lot. A lot of times when we're dealing with Wi-Fi, we are so focused on the RF, the channels, the proper design of the RF network, that sometimes we forget there's more to it than that. And so we're going to get into some of that technical stuff on Thursday. And today, our primary focus is going to be on understanding the different ways that we look at troubleshooting depending on where the problem might be in the stack. And today we're going to focus actually on the TCP/IP or DoD model instead of the OSI model, because that's what we all actually run. None of us run an OSI model, but we do run an actual TCP/IP model. So we're going to look at that. And I'm not diminishing the OSI. I think it has given us fabulous terminology that we use within the industry, but it all fits within the TCP/IP DoD model stack as well. So that's where I'll focus today. What I want to do first of all is talk a little bit about why philosophy matters. Why do we care about a philosophy of troubleshooting? The reason is because troubleshooting is a problem-solving discipline, and there is much research into problem solving. And I think that those of us that work in technology have not always taken enough advantage of it. And so since it's a problem-solving discipline, while we often think of it like a purely technical workload with commands and tools and configurations, it actually fundamentally relies on processes of inquiry, knowledge acquisition, decision-making, and these all have deep philosophical roots. So having a solid philosophy of troubleshooting can be extremely beneficial. Network engineers are practical, I like to say pragmatic, epistemologists. Now that's a word you probably didn't think you were going to hear today. Well, that's because troubleshooting is a form of applied epistemology. That's what it is. As network engineers, we're practical epistemologists. We're constantly seeking justified true beliefs, right? That great philosophical phrase about the state of our systems, which are complicated systems. So the process goes through a systematic cycle, and it starts with observation, where we look at the symptoms of a network malfunction. And then we might move on to evaluating the empirical data points that we got from our observations and develop hypotheses. And then we'll do some testing of those hypotheses and so forth to try to come up with our ultimate solution. So for our observation, we're going to do communication and observation. See, because this is all about information gathering, right? So we're not going to just observe the system, but we want to communicate and get input from the individuals involved in this. You know, there's this other minds problem where philosophers like to talk about, do any minds other than mine even exist? But the reality is that for us, the other minds problem is just we need to know what's in that other person's mind. You know, when they say, oh, the network's slow today, or Wi-Fi is not working, you know, well, okay, we need to get into that other mind and we need to find out what they mean by Wi-Fi is not working. The reality is their laptop's connected to Wi-Fi. They're checking their email. That's fine. They're using a database on the corporate network. That's fine. But when they're trying to get to a particular website, it doesn't work. Yet when they contact us with a trouble ticket, they say Wi-Fi is not working, right? That's the other mind problem. They're not thinking what you're thinking. And we need to understand what they're thinking, right? So after we communicate and observe, that's our information gathering, then we get into a do loop where we hypothesize, test, and evaluate. And we stay in that loop until we think we have a solid, strong hypothesis. And then we move on to resolve the problem. If, of course, the hypothesis failed to resolve the problem, then we might go back into our do loop again and pick the next hypothesis and then resolve again until we resolve the problem. But when we're done, we create what I call an epistemic record. In other words, we document. I've for years always been a big proponent of documentation, but I think this concept of thinking of it as an epistemic record might help you to be more motivated to do it, because epistemology is effectively the way we know what we know, the how of knowing. How do I know something to be true, right? And an epistemic record, therefore, is a record of the historic learnings that you've had. And guess what? If you and everybody else in your organization are creating, updating, enhancing this epistemic record, you start out with a strong foundation of epistemological knowledge that is based on pragmatic experience. That's valuable. That's super valuable. And here's the reality. You have a philosophy of troubleshooting. We all do. But do you know what it is? Is it consistent? Do you use the same one each time? Maybe learn from mistakes and improve it and get better? Does it work efficiently and effectively for you? Are there ways that you need to change your thinking about how you go about troubleshooting? This is why having a philosophy is helpful, because when you have a philosophy of troubleshooting, you can analyze it, you can determine if it's really effective in the real world, and you can tweak and tune it to work well for you. You can definitely have a general troubleshooting mindset and then a specific one for your network and your systems. And when you move to a different environment, you get a new job, you start doing a different role in the company, something like that. The reality is you may need to change up your philosophy a little bit, but that general philosophy will generally continue to hold true. So let's talk a little bit about epistemology. It's how we know, right? Leading to that justified action, because we have justified true knowledge. So epistemology is developed, our knowing is developed through our communication, as I said, and our observation and constraints and our hypotheses. Now, communication is both ingress and egress. In other words, it's coming into you and going out of you. So we're providing information to other parties and they're providing information to us. And both are required for effective troubleshooting. It's not enough for me to just talk. I might be an expert, but an expert can go down the wrong path if they're not actually dealing with the right problem. And so that's why getting information in the ingress of communication is important to us, even as experts. And then observation is both interactive and historic. And so, in other words, interactive observation means that we're actually getting into the system, trying to do something, and seeing what results we get, right? That's interactive observation. Historic is from a couple of perspectives. It can be looking at logs, and it can be looking at your epistemic documentation, right? So you are creating that documentation that you can rely on. So both of those fall into that category of observation. Many times when we think of observation and troubleshooting, all we're thinking of is looking at the current problem that's happening. But sometimes observation means looking back on past problems and what caused them, and we can learn from that. I won't go into long detail about it, but the example I often give is troubleshooting a problem 30 years ago. Wow. So troubleshooting a problem 30 years ago on one of the early Windows 95 machines we were rolling out. And it was actually almost 30 years ago this month. Windows 95 came out in August of 1995. And we started rolling it out immediately to some pilot users. Anyway, within those first couple of months, so it would have been either 30 years ago or maybe 1 month short, I had a machine. They were trying to run Microsoft Access. When they ran it, they were getting an error message that said a device attached to the system is not functioning. And I was the person designing all the standard baseline configurations for all of our Windows servers and clients. So I had to figure out this problem before we rolled out massively to, some 20,000 plus nodes on the network. And so I tried everything you would troubleshoot when you get an error message that says a device attached to the system is not functioning. I'm looking at hardware issues, right? I spent hours trying to find the problem. Before I went and did some historic observation, I searched at that time the TechNet knowledge bases that came on CD-ROM, I searched it for that exact error message. And I found one knowledge base article in TechNet that said, if you're getting the error, device attached to the system is not functioning with a Visual Basic 3 application, it could mean that the vbrun300.dll file is corrupted. And that was an enlightening moment, right? Yes, it was a CD-ROM, Lewis. Excuse me. I realized at that moment that there was no website then, by the way. Remember, this was 1995. We just started connecting to the internet really then in any big way over the next few years. So at any rate, I got to thinking, if a device attached to the system can be a software problem when that error comes up, maybe I'm actually dealing with a software problem here too. And indeed, that's what it was. It wasn't vbrun300.dll, it was some other DLL, but it was corrupted in access. And when I repaired that, everything was fine. And so that's an example of observation bringing in historic components. I can tell you that story sometime with the whole painful process in 20 or 30 minutes if you ever want to hear it. All right, the constraints. We have technical systemic constraints. This is basically where your network, your system that you've implemented, constrains the possible failure scenarios, right? There's this thing called FMEA, right? Failure Mode Effects Analysis. And it's where you build these failure trees where you say, okay, if this fails, here will be the results. And then if that causes this, then here will be the results. And so you've got these hierarchical trees of failure. And you're going to have a different FMEA tree for a Wi-Fi system in one environment than you would for a Wi-Fi system in another environment. There'll be similarities between them, but they will be different. This is what I mean by technical systemic constraints. The technology is limiting the possible failure modes and therefore failure scenarios or problem spaces that you're actually working in. Then you have economic or organizational constraints. These are things like your time pressures. You've got to get this fixed now. So you're going to start trying solutions as quickly as you can in many of those cases. You have limited access to information because of security. You have organizational policies that constrain what you can do in the troubleshooting process. So the point is that these kinds of constraints drive to what in pragmatic epistemology research they call satisficing. And you've probably heard that. Satisficing, it's a satisfactory solution that is sacrificed on the altar of our economic and organizational constraints. In other words, we probably could get a better solution, but we have to satisfice. We have to accept these constraints. Then you have epistemic and methodological constraints. This is about underdetermination problems where there are multiple equally plausible explanations for technical problems, and possibly you don't have the time to figure out for sure which one is the problem. So you try to go with the best solution that you think is right and you go with it. But there are many that are kind of on equal footing that could be the problem, and you're not quite sure where to start first. Then there's the theory-practice integration challenges where you're trying to bridge this theoretical knowledge to practical, contextual, situated knowledge. And that can be challenging, and that comes only through expertise over time. And then you have issues like trying to make decisions under uncertainty. This is called epistemic risk management requirements, right? And so the point is that these are those epistemic or methodological constraints. And I don't care if you remember what these are called. You just have to remember that these are all the things that are constraining your ability to gain and process knowledge. And then, of course, there's observability. We said observation is important, but sometimes you don't have the ability to access the information that you need for full observability. And then finally, with hypothesis, the thing that's going to have input to that knowledge development is going to be structural knowledge. Do you know how the system works? This is why, troubleshooting in our courses, if we have a troubleshooting section, it tends to be at the end. And the reason is because the you have to know how it all works before you can even think about troubleshooting it. You need that structural knowledge to be able to form hypotheses. And then your frames and models. These are your schemas, how you think about the network stack, the topology, the protocols, and how they behave and how they interact. If you don't have the right frame, if you don't have the right model, then you're going to have a hard time understanding it. And that's why we're talking today about using the 4-layer TCP/IP model. And if you want to use the 7-layer OSI model, that's fine. The point is that you need a frame of reference to think about it. And then there's experience in cases. This is what develops expertise, right? You can't develop expertise by just studying conceptual knowledge, what a lot of people like to call book knowledge, those kinds of things. You've got to actually work with technology to develop full expertise. Just like you can't watch somebody play the piano and become a master pianist, right? You have to get in there and do it. And so you will have your experiences, your case history, the things that you've worked on that will often cause you to just immediately come up with the hypothesis of what you think is the most likely cause of the problem. And then there's external cognition. External cognition means someone else has already thought about it and they're giving you input. This could be somebody else has already done some work on the problem. And so they have some things that they've gathered. They've done some of the information gathering, things like that. And you're going to let that pour into it. But it can also be your operational dashboards that show the status of different elements and components in your network and so forth. Your run books for how you're supposed to go about doing something and so forth. And that is where your hypothesis is born from. So all this stuff I've just talked about for the last few minutes tells you epistemology is important, but so is ontology. Ontology is the system. See, because ontology is how things work. Now, I'm talking here about the philosophical concept of ontology. I'm not talking about ontologies as models, like system models, where you develop an ontology of the system before you develop the system. That's a fictional or virtual representation of the real thing. In this case, I'm talking about the philosophical use of this term ontology, which means the real being, existence, or reality of the thing. And when it comes to our Wi-Fi networks, our things are systems. And a system is comprised of systems or system elements, right? And so the system interacts with other systems. It interacts with system elements. The system elements may interact with one another. And so there's this interaction that takes place. Nothing stands alone. Let's say you're in an environment where you have controller-based APs. Then the AP is a system and the controller is a system. And those two systems are using your network infrastructure, which is another system of systems, in order to communicate with each other, right? So this is astounding when you think about it, that you have systems of systems, but really you have systems of systems of systems of systems. That's the reality of what's going on when you're dealing with this information. And so, yes, it gets complicated. And that's why we need to study this ontology. But we don't just have that. Our systems of systems of systems of systems exist in an environment. And there's interaction among our system of focus, our Wi-Fi network, for example, and the environment, but there's also the interaction with the environment to the other systems that our system depends on. Yeah, I'm getting a little bit exacerbated here. Exacerbated? Exasperated. There we go. I'm getting a little bit exasperated because it can become very complicated very quickly. And that's why if you've watched many of my webinars or presentations, if you go to any of my training, systems always come up, and I always tell you, study systems theory and systems thinking, because it's going to help you a lot. Now, here's the thing. I want this to really sit home in the very heart of your system and become a fundamental foundational truth, what you might call a first principle. Every change to a network is a modification of its ontology. Think about that. It's like everything you eat changes your ontology. Everything you drink changes your ontology. Every time you move or sit stationary, it changes your ontology. In other words, your actual, real, existing being is changed by those things. And this is why it's so important in our more complicated environments that we deal with today. I mean, we're not just dealing with Wi-Fi. It's hard to be someone that just deals with Wi-Fi. You've got to understand, okay, am I implementing Wi-Fi in a controller-based architecture? And on top of that, is my network using VXLAN? Do I need to think about VXLAN and the impact that that might have for the VLAN IDs that I want to use for my SSIDs? And what are they using for the underlay versus overlay routing protocol? And how long does it take for the network to reach convergence? And well, you get the picture, right? There's so many concepts in the network that could be playing a role that impacts my Wi-Fi network. And we just go somewhere and we change one little setting, and we've just changed the ontology, possibly of our entire network. But if you change a setting for an AP, you've at least changed the ontology of that AP. So what is important today because of that? It's important that we have systems in place for managing all these systems. And that's why the concepts of software-defined networking, infrastructure as a service, or infrastructure as code, infrastructure as code, it can become a very important concept. Because with infrastructure as code, without going too deeply, because it's not our topic today, basically the only way configuration changes happen is that you change the configuration code that defines those configurations. And what that does is it helps to avoid configuration drift, where you end up with, one set of APs configured one way and another set another way, and there's no real reason for it. It's just that you had to do some troubleshooting. You solved a problem and you fixed it for that one set of APs that are managed by the controller. But for the other set of APs, whatever the vendor calls that way to collect APs together, right? For the other set of APs, you didn't make the change, even though it wouldn't have hurt if you'd made the change, and it might have prevented that other set of APs from having the same problem in the future. The point is you have configuration drift now. Now, it's maybe that you don't want to change that other set of APs, but it's something that you always have to think about. Is this something that now needs to become a preventative action, something that I need to take action now after I've solved this problem so that I don't run into new problems in the future with other systems? And infrastructure as code helps with that. Infrastructure as code is primarily focused on your infrastructure devices, routers, switches, controllers, APs, those kinds of things. And then configuration as code, it might be thought of as being used related to all of those, but also goes up the stack to the applications and things like that you're running. The point is you're using DevOps concepts to manage your network. Maybe you're using things like Ansible and other automation solutions that help you to push out these configurations. But the point is that you realize this core first principle: every change to a network is a modification of its ontology, and then you make adjustments. Now, the next thing I want to talk about from a philosophical perspective before we get into the TCP/IP model is a brief overview of pragmatism, because the philosophy that I'm sharing here of network troubleshooting is based on epistemology, ontology, and pragmatism. Now, pragmatism is an area or a way of conceptualizing knowledge based on effectiveness or efficiency or practical application of that knowledge. In other words, you look at the results of an action and not just the action itself. You look at what the knowledge gets you and not just the knowledge itself. So that's pragmatism. Practical problem solving then, meaning is use. To understand a concept, ask what difference it makes in practice. So Charles Peirce, a philosopher from the late 1800s, early 1900s, called this the pragmatic maxim. So for every concept we want to understand, we're always asking, what difference does it make? Why do I care? It's kind of like what we try to do through our learning materials where instead of just telling you, flip this switch in your controller, we want to tell you, what difference does that make? How does that change the functionality of the Wi-Fi network? Truth as inquiry success. A belief counts as true if it survives open-ended community testing and keeps working reliably over time, not just whatever works for me today. This is why I say community is so important for people in engineering and technology professions and in the Wi-Fi space too. We have a great community in Wi-Fi. It's not massive. We don't have 25,000 people that show up at a Wi-Fi conference like some other conferences might have, but the ones that show up care about Wi-Fi and they care about each other. And that community is important. You know, you think you've got an idea for a great new solution for wireless situations? Talk to people about it in the community, or put your thinking together, give a presentation at WLPC, and let people give you feedback on that presentation. And don't take it negatively if someone comes up and says, I disagree with this part of your presentation. I mean, I know all of you agree with me 100% with everything I say, but the reality is that not everybody agrees with everybody all the time. And of course, you don't all agree with me all the time either. And that's wonderful because that's truth as inquiry success. It's about exposing your ideas to other people, running it by other people. It's why I say if you're just starting out in the industry, get a mentor. And you might say, well, I don't live near anybody. I don't really feel like I can have a mentor because I don't live in a situation to have that kind of communication. Well, there's a Slack channel out there that you can find out about. Just ask around. They'll get you into it. It's super secret, like the old pirate BBSs back in the 80s and 90s. Very, very hard to find out about it. But no, if you ask several people, they'll tell you how to get into that. CWMP doesn't run it, so I don't generally give out all the details, but it is something that is useful to you. There's social communities. Twitter used to be really popular. Now X seems to have winded down somewhat in recent years. But I've noticed over the last maybe 6 to 12 months, LinkedIn has gotten really, really popular. A lot of you have been posting really good things on LinkedIn, and that's a great place to connect with people. And the point is, just go out and put a post on LinkedIn. Say, here's what I'm thinking. What do you guys think? And someone will usually post back. And then there's fallibilism. This says that all claims are revisable. We improve beliefs by experimenting, comparing outcomes, and correcting errors. You think you understand how something works? Test it in the real world. Implement it, and then do protocol analysis. Capture logs. Look at the processes and see if you're right. And then evaluate your thinking and change it. Anti-foundationalism says there shouldn't be any belief that's beyond revision. Justification comes from coherent fit with experience and other well-tested beliefs. And then instrumentalism. Theories are tools for action. Or you could say hypotheses are tools for action. Choose the one that best guides effective interventions. The whole point of a pragmatic approach to troubleshooting is that you're looking for the solution that is giving you the best end result in your environment. Not necessarily the quickest, not necessarily the easiest, but again, remember, we always have constraints that we have to bear in mind as well. And finally, there's pluralism. Different contexts can warrant different useful descriptions, so long as they earn their keep in actual implementation. Actual praxis. Praxis is basically practice, the doing of something, but it has that added meaning of beyond theory. You'll hear phrases like from theory to praxis. It's a fancy way of saying doing, but with this connotation in mind that we're saying doing as opposed to just thinking about it, right? And it provides a salient standard for assessing the adequacy of hypothetical solutions. Now, is pragmatism right for everything that you want to think about in life? I personally don't think so. Maybe you do, but I think it's a great philosophy for troubleshooting. Now, there are a couple of fundamental truths that we have to think about here, and they are parsimony and first principles. So parsimony simply means that you're going to apply Occam's razor, right? The way this is oversimplified is usually the simplest solution is the best. It's a little more complicated than that. You're talking about breaking things down to its fundamental, simplest components in order to focus on the right way to think about or analyze something. But parsimony, or Occam's razor, the simplest solution is always the best, is a simple way to think about it. And then first principles says that we're going to look at the elemental components that make up this system. And instead of reasoning by analogy, we're reasoning by fact. In other words, we're looking at how it actually works. What is the foundation of the functionality of this technology that I'm dealing with? And then we're troubleshooting from there. So you could wrap it all up by saying that the methodology says we need to do our information gathering, then our hypothesizing, testing those hypotheses, and then choosing the best solution and going with the pragmatic intervention. Remember, it's the thing that gives us the good outcome. It's pragmatic. That's why we're going after it. And verification and prevention. So verification that it worked, but then also looking at, are there any problems that this change might cause? So I want to go ahead and address those. Or do I need to distribute this change throughout for consistency and prevention of configuration drift? And then I go back to my epistemic record. That's right. I called documentation that again, because it is my epistemic record that I can go back to. So I'm starting with a foundational epistemology or set of knowledge before I even begin gathering new information. So how does all this fit with TCP/IP? Well, RFC 1122 defines the 4-layer model of TCP/IP. And you could say that this is the TCP/IP ontology. It begins with the link layer or network layer, which comprises basically the physical and network layer, or the physical and data link layer of the OSI model. And then we have the internet layer, or IP or IPv6. And then we have the transport layer, or TCP or UDP. And then we have the application layer. Now you might notice this kind of looks like an hourglass. Well, that's intentional because that's exactly the architectural philosophy behind the internet architecture. There's a concept within the internet architecture thinking that came out, a couple of concepts that came out in the 80s in some research papers, some published papers that attributed to, that spoke to the way that all of this evolved from the late 70s to the 80s. And they were a thing called the end-to-end argument and the shared fate concept. So the end-to-end argument basically says that complexity needs to be in the ends and not in the middle. And the shared fate concept says that the two ends are sharing their fate only with each other. In other words, in between the two endpoints, things can change in the network topology. There might be a delay, there might be a slowdown, but if that topology between the two ends is self-repairing, then eventually the two endpoints can resume. So the only thing that in that kind of a fault-tolerant, redirectable, repairable IP layer, if that kind of thing is there, then the only thing that can break the connection, the session, the established link between those two endpoints is one or either of the endpoints. So if the endpoint fails, then they share the fate. They're both now failed in relation to their connection with each other. So that's this shared fate concept. And then again, the end-to-end argument says that complexity should be in the ends. So how does that apply? Well, the way that applies is that up here at the application layer, notice things are bigger. Down at the link or network layer, notice things are bigger. But as you get to the middle, they're narrower. So our user and support protocols providing application functionality, we have many more of those and much more complexity in them. TCP and UDP are going to be a little less complex, but they're more complex than IP. Well, TCP is more complex than IP and provides for this shared fate model. And then the internet layer is really just a best effort and a stateless model. This is why they went with a packet switching model in the development of the network, so that you could be redirected on a new route if something fails on the route. And then the link and network layer are more complex, and some are more complex than others. Wi-Fi is obviously more complex than Ethernet. And so the key is then that layered troubleshooting indicates you're ensuring proper operation at each of these layers, and you're targeting the likely layer first, which would be divide and conquer, or you're working bottom up or top down in your troubleshooting process. So what's in this hourglass, and why is the top and the bottom bigger than the middle? Well, because at the top, we have HTTP, HTTPS, QUIC, DNS, SMTP, IMAP, FTP, SIP, RTP, NTP, DHCP, SSH, SNMP, and technically routing protocols, because they work across TCP or UDP, but they are a protocol above it. And then at the bottom, we have Ethernet, Wi-Fi, 802.15.4 and all its variants, LoRaWAN, Z-Wave, PPP, PPP over Ethernet, etc. So we have all of this at the bottom. But in the middle, we have either IPv4 or IPv6, and we have either TCP or UDP in the vast majority of all communications that occur. And what the hourglass model suggests is that there's this thing called a spanning layer. And the spanning layer is what goes across all of the interconnected networks. So our spanning layer is IPv4 and IPv6. Now, the goal of the hourglass model and the spanning layer is that you would only have one protocol used across that entire spanning layer. But due to transitions, you might have two during some window of time. Well, for a very long window of time now, we've had two, and that's IPv4 and IPv6. So when you know the ontology of TCP/IP as a stack, and not just as TCP and IP, but the whole model for how it works. Because when you're thinking about the TCP/IP model, you're not just thinking about TCP and UDP and IPv4 or IPv6. You're also thinking about what's above TCP and UDP and what's below IPv4 and IPv6. Because in the DoD model or the TCP/IP model, while they're not defined in some of them are in IETF standards, the generally what's below it is not, but what's above it is. Then you've got to know how these things work so that you can troubleshoot the problem you're facing. So as a person primarily dedicated to Wi-Fi, you're probably going to spend more of your time studying 802.11 and less of your time studying 802.15.4 or even Ethernet in detail. You'll probably just know the fundamentals of that, although I would encourage you to know more over time. And you're probably not going to become a guru of the application layer stuff, but there'll be some of the application layer things you need to, like NTP, right? Or SNMP, or things like that that impact the administration and management of your network. But when you understand how things actually work, then you are understanding the being, the existing, the way these things exist in the world. And this is the hourglass model, and why we talk about troubleshooting up the OSI model or down. But in this case, I'm talking about the actual model we implement instead of talking about the OSI model. We also have to think about what are the ontological differences, the way these things exist differently when they are these different lower layer protocols, like Ethernet versus Wi-Fi. I'll just give you a quick rundown. Ethernet, no connection. Wi-Fi, there is a connection. Now, I'm obviously not talking about physical wires here, right? I'm talking about, are we establishing some kind of a connected state? Think of it like the fact that TCP creates a connection before communicating, and UDP does not. UDP just starts dumping to a destination IP UDP port combination. And TCP doesn't. It does the three-way handshake first, right? So that is your connection process. That's interesting. So Dan says that he checked with ChatGPT, and ChatGPT says Wi-Fi is about 250 times more complicated than Ethernet. Well, be careful, because they might just do it by page count, and then they'll come back to you and say, well, Ethernet has more than 10,000 pages in the standard, and Wi-Fi only has about 5,000 pages in the standard. But the difference is That 10,000 pages in Ethernet has pages for every different PHY, like 10 megabit, 100 megabit, gigabit, 10 gigabit, 40 gigabit, 100 gigabit, et cetera. And then all the different types of PHYs that can be done at those different data rates. It's got all of those that have to be in there. Whereas Wi-Fi is more complicated in how it actually communicates on the network. I don't know about 250, but I think that's probably pretty close. Might be a bit of a hallucination, but it's pretty close. All right. Usually no authentication in Ethernet, hopefully authentication in Wi-Fi. Now, I have to say usually because, you might be using 802.1x on some of your Ethernet connection ports. And with Wi-Fi, you're not always using it, though that's going to change in the coming years. And, maybe 20 years from now, for example, we'll only use OWE or whatever its successor might be in all bands that use Wi-Fi. Assumed delivery in Ethernet. Have you ever thought about that? Ethernet doesn't verify delivery like Wi-Fi. There's no ACK that comes back after an Ethernet frame is sent. If an Ethernet frame is sent from a device to another device and the receiving device sees that it's corrupted, it just drops it. And it's just, Ethernet just says, it's all right. Something at a higher layer will take care of it, which happens to be TCP probably. But there's no verified delivery. With Wi-Fi, there is, because we have to deal with how the Wi-Fi channel actually works. We have drop-on error on both of them, though. So this is where it gets interesting. Well, wait a minute. You just said there's verified delivery with Wi-Fi. There is. But both of them drop on error. It's just that Wi-Fi acknowledges if it is received. And because of that, if the receiver dropped on error, then the transmitter retransmits after the retransmission timeout. And so that's a big difference in how Wi-Fi works over Ethernet. No retries with Ethernet, but there are retries with Wi-Fi. No fragmentation with Ethernet, but you could have it still with Wi-Fi. Consistent local link, completely inconsistent local link. And this is just a beginning of a comparison. We could create a list probably 5 times this long of the ontological differences, the actual real differences of how these two things work. And this is just comparing Ethernet and Wi-Fi. You could do the same thing by comparing Wi-Fi with 802.15.4 or comparing Wi-Fi with Z-Wave or Wi-Fi with Bluetooth and on, right? There would be these ontological differences. So I'm using this fancy term ontology, but what I'm saying, you got to know how it exists, how it works, how it functions, how it is in the real world if you're going to be able to successfully hypothesize solutions to problems. And then you need to know the tools to use at each layer of the overall TCP/IP ontology, if you will, the application, transport, internet, and link layers. So the link layer tools, you can have your protocol analyzers, of course, your spectrum analyzers, cable testers, command line or shell tools like NetSH, though it is deprecated. I always like to tell people it's going away someday. ifconfig, ethtool, PowerShell. These are all things that you can use to find out about layer 2 and below to some extent with command line tools. You have your link lights, LEDs, and system errors, looking in the logs of your system files. These are your link layer tools. You have internet layer tools. Guess what? Again, protocol analyzers, command line and shell tools like ping, traceroute or traceRT on Linux. Path ping on Windows is a great alternative to traceroute. ipconfig, ifconfig, ARP, route, netstat. These are all command line tools. And you still have your system errors. And then you've got your transport layer tools. Guess what? Protocol analyzers. Notice they keep coming up. And then command line and shell tools. What you could use here, you can use Telnet to just do like a quick test for TCP reachability, even if it's not a Telnet server at the other end. You can use curl. It can verify that you're communicating or able to communicate across HTTP or HTTPS. You can use SS, netstat, iperf. Someone just mentioned NC. There are a lot of different tools. And then you have your network scanners as opposed to protocol analyzers. So now we're talking about Nmap, for example, right? The most common one. So Nmap is a scanner that checks to see if ports are open, checks to see what hosts are alive on the network. But if you're taking it to that level of actually trying to do service discovery and fingerprinting, then you're dealing with transport level communications. And then, of course, system errors. So there are two that are always here. Of course, the command line and shell tools are always here, but the ones that are consistently the same thing are protocol analyzers and system errors. And then application layer tools. Your protocol analyzers are back again, and other command line tools. You can use curl again here, SSH, OpenSSL for testing your secure remote connections, NSLookup for DNS testing or DIG, FTP or FTPS or SFTP tools, LDAP search for querying your directory and finding out why radius authentication is not working, seeing if LDAP's functioning, that kind of thing. And guess what? We have system errors again. And then you have your full stack tools. So what do you think is going to be on this list? Things that work across the entire stack: protocol analyzers, and system errors. So what does this tell you? It tells you that some of the most valuable tools you can learn to use are protocol analyzers and let's call them log aggregation and analysis tools for simplicity. You know, you've got security information and event management or SIEM tools. You've got syslog services that can aggregate logs from multiple devices. And then you've got, you know, things like Grafana that you can use to build dashboards based off of your logs. Splunk can also be used, it was just mentioned by someone in the chat, to create log dashboards and things like that. These are all examples of working with system errors, and that's what I want to encourage you to think about. You know, you can go back to your team and say, how do we centralize and aggregate our system errors so we can have a more meaningful solution to troubleshooting full stack problems, so that we can anywhere, at any time, go in and look for possible problems that span our entire network. But there's another tool as well that some people don't know about, so I'm going to share this into the context of full stack tools, and that's trace files in Windows operating systems. These can be very, very useful to you because they give you insights into everything that's going on in the network stack in that system. So trace files are going to be implemented using a command line tool in Windows called pktmon or packetmon. pktmon can create, well, first of all, it can capture your packets, and then it can just dump a pcap file effectively. But you can have it not just capture packets, you can have it also capture Windows events. And there are dozens of Windows providers that are available to you that you can call on. And some of them are, for example, a Wi-Fi provider. So you can get insight into the Wi-Fi environment. For example, you can see when it scans for networks, what networks did it find at the low level? And then when it connects to a network, what were all the characteristics of that network and what signal strength is it getting, and not that garbage one that you get at the command line in NetSH when you look at signal strength, which is not dBm, but it's some other value that Microsoft likes to give you, and you can roughly translate it back to dBm, but not exactly. This is an actual, from what the radio can give to the system, the dBm value for the signal strength. And that's in there. And then you can see even when it's connected, when it's scanning for other networks it might want to roam to, all that kind of stuff, it's in there. And then you can use Message Analyzer, but the trick here, you got to go to the Wayback Machine to download it because Microsoft doesn't support it anymore, hasn't for over 5 years. And but it still works with trace files, even Windows 11 trace files. So you can read them in there. You can do it in Wireshark. A lot of people don't know that, but if you pay attention when you're installing the newer versions of Wireshark these days, there's an option to install a trace file viewer. And if you do that, it's just built into Wireshark, but it makes it so you can view trace files. Or you can just use pktmon to export them to a raw text file, and then you can open it up and look at it in that way. So these are some useful tools for that troubleshooting process for the full stack. All right, applying the philosophy. Case 1, users report sporadic connection drops, high latency, packet loss, and network timeouts. The issues are particularly challenging because they're not constant, appearing and disappearing unpredictably. So how would you deal with that? Well, it's an intermittent problem, right? And that gives you some, let's use the fancy term, epistemological challenges. Why? Because knowledge acquisition is hard. You're going to have to monitor over a period of time to capture that window if you don't have existing systems that have already done it for you. This is why I said, if you've got some kind of centralized logging solution, if you've got a centralized monitoring solution that monitors your network and allows you to roll back in time and see things in the past, maybe they let you see what the spectrum looked like in the past, or a sampling of a protocol capture in the past, these kinds of things. So you really need to think about the ability to go back in time. And that means that you're archiving logs and any kind of data that can be useful for troubleshooting so that you don't have to wait till it happens again. In other words, you can go back and look at it having happened in the past. So when you're thinking about the epistemological issue here, getting knowledge, you understand quickly the value that is brought by having these types of overlay systems that harvest this knowledge for you. And we'll leave that as enough said for case 1. What about case 2? Users experience reduced data transfer rates across the network, leading to slow web browsing, video streaming, and overall application performance degradation. It's a common system that can stem from many underlying root causes. So what do? Well, first of all, you need to understand capacity. Keith spends a lot of time talking about the importance of capacity. And you need to understand it, both from a conceptual viewpoint and from a practical, technical, ontological viewpoint of how it works in the real world. And only then can you begin to analyze these issues. And that's where we're going to talk about a bit of the ontology of TCP. How does TCP really work? And I'm not just talking about what you see going back and forth on the network, but how it thinks inside of itself and makes decisions. And we're going to talk about that when we look back on these issues again on Thursday. So, what could cause this? Well, it could be network congestion. And, Wi-Fi introduces a new network congestion problem. So we had a network congestion problem with early Ethernet where there was a shared medium for all the devices on the bus, right? When we did a bus topology. But then we went with the star topologies and eventually got away from hubs to switches. And now you don't really have a congestion problem between your end device and the switch. If there's a congestion problem, it's somewhere later on where the problem exists. With Wi-Fi, we also have congestion problems on the local link, don't we? It's called contention, possibly even interference, because in other words, we can still categorize it as congestion when it's interference if it's another valid communicating system and it's not just some machinery interfering or something like that. Something's using the channel, even if we don't recognize it as a Wi-Fi device, it's still a valid use of the channel, right? Bluetooth is a valid use of the channel. Zigbee is a valid use of the channel. And so that's still, the channel is congested by things using it. That's what congestion is. More things using a channel, than the capacity of that channel. Okay. And so that's a common problem in these situations. Well, let me wrap up leaving you with this. Quoting from RFC 1958, June 1996, the principle of constant change is perhaps the only principle of the internet that should survive indefinitely. And I think they had a point some 30 years ago. And the reality is, why am I quoting from a document related to the internet? Because what we've done since 1996 is we've taken the internet and made our networks the internet. In other words, on large-scale enterprise networks, we have dozens, maybe hundreds of routers, layer 3 switches, etc. And we're dealing with internet on our network. It's like we have our own autonomous system internet connected to the internet, which is connected to other autonomous system internets and so forth. And yeah, it's quite a wild thing. And therefore, that's what we're troubleshooting when we're troubleshooting Wi-Fi up and down the stack. We're troubleshooting our own local internet is what we're doing.